Hello everyone, welcome to new class. Today's class is about diode applications. Most electric supplies provide alternating currents rather than the DC current, and available electrical supply at the consumer terminals is AC. And one of the important reasons being AC is more easily generated and transmitted over long distances, but most of the electronic devices and circuits need DC voltage for their operation. And the most convenient way to change AC to DC is by means of rectifier. The process of converting AC voltage into DC voltage is known as rectification. And this is the block diagram of a regulated DC power supply. So, the transformer steps down the AC supply into AC voltage of required level, and it is given to a rectifier. The rectifier converts AC input voltage to a pulsating DC voltage. So here the output is pulsating DC, and this is passed through a filter, and the filter eliminates the fluctuations in the rectified voltage and produces a relatively smooth DC voltage. So here we get a smooth DC voltage, and the regulator is a circuit that maintains a constant DC voltage. So the output of regulator is constant DC voltage for variations in the input line voltage or in the load. So let us study about the rectifiers. The rectifiers are of three types: half wave rectifiers, full wave rectifiers, and bridge rectifiers. Let us study about half wave rectifier. The circuit diagram of a half wave rectifier is shown in the figure. It consists of a transformer, a diode, and a load resistor. The primary coil of the transformer is connected to the AC mains, and the secondary coil to a load resistor RL through the diode D. And this is the input voltage we applied. So during the positive half cycle, that is, this is positive half cycle. So during the positive half cycle of the input voltage, the diode D is forward biased and it conducts the current through RL. So we can draw the output as, so it will be like this. And during the negative half cycle, that is, this is negative half cycle. So during the negative half cycle of the sine wave, the diode D is reverse biased, hence no current flows in the circuit. That is, during positive half cycle it will be like this, that is closed. It will be like a short circuit, and during the negative half cycle the diode will be open. So no current flows in the circuit and no voltage develops across RL. So here we will not get any wave. Again in the positive half cycle the diode conducts, so it will be like this. Negative half cycle, no current flows. So the output voltage waveform will be like this. And only the positive half cycle of the input appears across the load. The output voltage contains a DC component. So it contains a DC component as well as an AC component known as ripple. So ripple is the AC component present in the output of the rectifier. Next is peak inverse voltage. During the negative half cycle of the input, the diode is reversed. All the input voltage now appears across the diode because it is open. So the voltage across the diode is maximum when the input voltage is maximum. So the maximum reverse biased voltage that appears across the diode during the negative half cycle is called peak inverse voltage. So for a half wave rectifier, peak inverse voltage is equal to the maximum voltage of the negative half cycle, and which is equal to Vm. Next is average values of output voltage and load current. Let V is equal to Vm sin omega t, or we can write Vm sin theta, be the instantaneous sinusoidal voltage appearing at the secondary coil of a transformer, and if Vdc is the average or DC value of the output voltage, then we can write Vdc is equal to area under the curve over the full cycle divided by base, and that is equal to area under the curve over the full cycle is, we can write integral over 0 to pi, because in the output we have only the positive half cycle, so 0 to pi v d theta divided by the base is 2 pi, and that is equal to 1 by 2 pi integral 0 to pi Vm sin theta d theta, and that is equal to Vm is constant, Vm divided by 2 pi, then integral of sin theta is minus cos theta to the limit 0 to pi. So we get Vm divided by 2 pi minus cos pi. Cos pi is minus 1. So minus of minus we get 1. Then minus cos 0 is 1. So minus cos theta. Then we get minus 1. And that is equal to Vm by 2 pi into 2. So we get Vm divided by pi, or we can write 0.318 Vm. So the average value is Vm divided by pi in the case of half wave rectifier. And average value of the load current IDC is equal to VDC divided by load resistor, then that is equal to VDC is Vm divided by pi into RL, and Vm by RL we can write Im is equal to Vm divided by RL, so this we can write Im divided by pi, so IDC is equal to Im divided by pi. Next is RMS value of load current. So IRMS we can write square root of integral 0 to 2 pi I square d theta divided by 2 pi, where I is equal to Im sin theta, and that is equal to square root of 1 by 2 pi integral 0 to 2 pi I square is Im square sin square theta d theta, and that is equal to square root of 1 by 2 pi, then integral 0 to 2 pi Im square we can take outside Im square. Then sin square theta is 1 minus cos 2 theta divided by 2 into d theta, and which is equal to square root of Im square divided by 2 pi. Then we can split this limit, that is integral 0 to pi 1 minus cos 2 theta divided by 2 d theta, then plus integral pi to 2 pi. So the negative half cycle value is 0, then d theta, and that is equal to square root of Im square divided by this 2 we can take here, so we will get 4 pi. Then applying the integration, we get the integral of 1 is theta, then minus integral of cos 2 theta is sin 2 theta divided by 2 to the limit 0 to pi. Now we can apply the limit, that is square root of Im square divided by 4 pi into applying the upper limit pi minus sin 2 pi is 0, then minus applying the lower limit 0, so we will get 0, and that is equal to this pi we can cancel, so square root of Im square divided by 4, so we will get Im divided by 2. So IRMS, the RMS value of the load current is Im divided by 2. Also VRMS equal to Vm divided by 2, and this is equal to 0.5 Im. And we can conclude that IRMS is greater than IDC. Next is ripple factor. The output of half-wave rectifier is unidirectional but fluctuates greatly with time. Hence, the output is pulsating DC. So, output of rectifier is pulsating DC. That is, it contains DC and AC components. The undesired AC components are called ripples. And ripple factor is a measure of purity of the DC output of a rectifier. And ripple factor is defined as the ratio of RMS value of the AC component of the load current or voltage to the average value or DC component of the load current or voltage. That is IAC divided by IDC or VAC divided by VDC. And the ripple factor is denoted by the letter gamma. So we can write the RMS value of current IRMS equal to square root of IDC square plus IAC square. From this we can write IAC is equal to square root of IRMS square minus IDC square. So the ripple factor is gamma. Ripple factor gamma is equal to IAC divided by IDC, and that is equal to square root of IRMS square minus IDC square divided by IDC, and that is equal to, by rearranging we get IRMS square divided by IDC square minus 1, and IRMS is equal to Im by 2, that is Im divided by 2 divided by IDC is Im by pi, the whole square minus 1 square root. So here Im we can get cancelled and we get pi square divided by 4 minus 1, and that is equal to, after calculating we get 1.21, that is gamma is equal to 1.21. Since gamma is greater than 1, it shows that the RMS value of AC component of wave is greater than DC value of wave. Hence, half-wave rectifier is a poor device for the conversion of AC voltage into DC voltage. Next is voltage regulation. The regulation is a measure of the variation of the DC output voltage as a function of the DC current and is defined as percentage regulation is equal to voltage V no load minus V full load divided by V full load into 100. And for an ideal power supply, the output voltage is independent of the load resistance and hence percentage regulation is 0 for ideal power supply. Next is transformer utilization factor, TUF. It is defined as the ratio of the DC power available at the load resistor to the VA rating of the secondary coil of a transformer. VA rating means the apparent power. So we can write TUF is equal to DC output power divided by apparent power, and the transformer utilization factor for a half wave rectifier is 0.287. So that is about the half wave rectifiers. In the next class, let us discuss about a full wave rectifier. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.